Hello, I'm Darren Llewellyn. Welcome to another episode of MyToolboxTV. Today we're going to talk about motor nameplate data. It's a very important part of the motor. If you're going to size the motor, get motor starter heaters, fuses, wires, all kinds of stuff, you got to access the motor nameplate data. Let's take a look at it. Motor nameplate data is critically important when you're doing maintenance work or electrical installation work. The motor nameplate has all information about this motor, and the nameplate we've used as an example is for a three-phase induction motor. It's dual voltage, 230, 460 volt, and it's a 10 horsepower. Pretty common motor, and these are, even though we made up the nameplate, MyToolboxTV doesn't actually make motors, but the numbers are actually real from a real motor. Let's take a closer look at the top part of the nameplate, a catalog number and specification and some other stuff. The top part of the nameplate, the first thing on this particular nameplate is the catalog number. That's a manufacturer-specific number. If you're going to reorder this thing, it tells you exactly what you're going to get. The spec number, the next line, is also manufacturer-specific information, tells you all kinds of things about this particular motor. The serial number over here, this WO549, is also specific to the manufacturer, and it gives you information like when it was made, what shift perhaps, what plant, all different things like that. It's manufacturer specific. Frame, this frame size right here, this is a 215T frame. That gives you mechanical information about this particular motor. It's not got electrical information there. Along with this 215T frame, you can look this number up, and along with the charts comes a drawing. And let's take a look at one of those drawings. This is a standard chart that you would see used for the frame size. What you end up with is a chart that has different columns. Every column is a mechanical dimension on the motor. Accompanying all of these tables, these charts, will be a drawing of that motor showing what each dimension means. Like shaft height, for instance, is drawn out, hole patterns, those kind of things. And if you go down and find your motor, you would find every dimension. There's the 215T, every dimension that's called out on that motor. Here's what the accompanying drawings might look like with that frame size chart. I realize it's kind of hard to read on this video, but you'll find these in motor books. You'll find them in NEMA books. These are NEMA frame dimensions. NEMA is the National Electrical Manufacturers Association, kind of the police on the motor nameplate data. Different dimensions, like here for one, for instance, is dimension D, and that's the shaft height. Dimension 2F is the hole pattern lengthwise on the motor. Let's take a look at what those equate to in the chart. If we look at a chart, 215T is right here, and dimension D, that was the shaft height, is in this column. So the shaft height of a 215T motor is 5 1/4 inches. I think we also looked at dimension 2F, which was the hole pattern down the length of the shaft. Dimension 2F for that particular motor is 7 inches. So using these tables, you would even know if you had to drill motor mounts and mount the motor, you would know exactly where the holes would need to be. So all of this is just mechanical information. It's not electrical stuff, although you can tell some electrical stuff, like if the shaft height is 3 inches compared to a shaft height of 8 inches, you know that the 8-inch motor's, that motor is going to be a big one. Just about the most important piece of information on the motor nameplate for me anyway, the place I look at first, is the horsepower. That's basically, simply put, how much work this motor is going to do. There are standard horsepowers. 10 happens to be one of them. You're not going to go out and buy some crazy, 12 2/3 horsepower motor. There's standard horsepowers, and you can find out what those standard horsepower ratings are from NEMA. You can find that on their website. The next line is voltage. This particular motor is dual voltage. It's 230 and 460 volts. Now right below the voltage you'll see the amperage. And you'll see it says 25/12.5. The 25 is the current that this motor will draw at 230. The 12.5 is what it draws at 460 volts. You can see if you increase the voltage, the current cuts in half. And that's because the horsepower stays the same. Horsepower can be, there's a 746 watts electrical power consumed per horsepower, and that stays the same. Stays the same by the way we connect the motor. The connections for this motor, you'll see there's high and low. This is a standard US 9-lead electric motor. 9 leads are labeled T1 through T9. Now, by looking at this motor, I can tell that this is a Y-connected motor by the way the connections are made. If you want this motor to run at 230 volts, which is the low voltage, you hook T4, 5, and 6 together. And then you hook T1 and T7 together and hook that to L1. That's the phase lead. T2 and T8 together and take that to L2. 3 and 9 together and take that to L3. So this is your 3-phase incoming power. And that's how you would run this motor on 230. For 460 volt operation, you go to the high connection and you hook 7 and 4 together, 8 and 5 together, 9 and 6 together. That would be inside the connection box. And then take T1 to L1, T2 to L2, T3 to L3. And that's how you get this to run on the high voltage, which in this case is 460 volts. I remember when I first learned about 3-phase motors, I couldn't figure out why when you increase the current, or when you increase the voltage, the current went down, because I just learned Ohm's law. And Ohm's law said if you increase the voltage, the current's going to go up. Well, here we're actually changing the circuit. We're changing these connections so the circuit remains 10 horsepower. So we're keeping the wattage the same. When you do that, if you increase the voltage, the current has to go down to make the math right. And so that's what happens. There's lots of advantage to running this motor on 460 volts rather than 230, and one of those is wire size. It's going to 12.5 going to require, smaller wire than 25 amps would, and a smaller breaker, and less heat loss in the conductors going out to the motor as well. Next thing I want to look at is the RPM. In this case, the RPM is 1760. That's a standard RPM. The motors, you look at the motor catalogs, you'll see all the motors are 1760, 3450, things like that, and it's all derived from the number of pole pairs in the motor. The next thing I want you to look at is the frequency. Hz stands for hertz. That's how many cycles per second this motor is designed to run at. 60 hertz is what's standard in the United States, and at 60 hertz this motor will run 1760. If you're running this through an AC drive of some kind, what you will do is lower that frequency or raise that frequency, and that will change the speed of the motor. So the speed is all determined by this frequency. This is also a 3-phase motor. The PH stands for phase, and it's a pretty common motor. Next thing I want to look at is the insulation class. This is insulation class F. There is a corresponding table from NEMA, and they tell you what that means, and it tells you what temperature that the insulation for this motor will withstand. F is a pretty common one. H is for really high temperatures. So that tells you what kind of temperature this motor can operate at. Next line we have service factor. This is a service factor of 1.15, common service factor for motors of this size. 1.15, the service factor is how much this motor can do above its rating without overheating. So this motor will actually do more than 10 horsepower worth of work for an extended period of time without causing overheating. The NEMA design, design letter B, that's a very common design letter. The NEMA design, you can find this information on NEMA's website, National Electrical Manufacturers Association, NEMA.org. The design B tells you what type of starting current, what kind of torque, what kind of slip that this motor might have. So if you're replacing this motor, make sure that these numbers are the same. The code letter over here, G, that refers to the locked rotor KVA. That's kind of a thing engineers would care about when sizing this motor and also sizing other things, feeding this motor. Not something maintenance folks have to worry too much about. Down here, you've got nominal efficiency, NEMA nominal efficiency, 91.7. That means that we're using and consuming for work, real work we meant to do, 91.7% of the energy that this motor is consuming is actually going to real work. The rest of it is being wasted by heat in the conductors, magnetic fields causing currents in the laminations, I squared R loss, lots of other kind of things, just inefficiencies inside the motor. You ever put your hand on a three-phase motor while it's running, you feel it's kind of warm, and that warmth is where the rest of this goes. It's creating that heat, and that heat can also be coming from the mechanical inefficiencies. Just if bearings get hot, it means you had to consume electrical power to heat up those bearings. Enclosure. This is an open enclosure. The enclosure is an open motor. That means it's not submersible. It's not a wash-down duty motor. It's an open motor, free to the environment. The rating down here, 40 degrees C ambient, means that all of these numbers up here are based on no greater than 40 degrees C ambient temperature. If this motor is put in a higher area than this, then these things have to change up here. The motor will get hotter. The motor will change its characteristics. It's a continuous duty motor. Continuous means that this motor is designed to be turned on and left on. It's one of those motors that you just see running all the time. It's never turned off. Maybe it's a pump or a fan or a conveyor, something like that. There's lots of other kinds of duty motors, like intermittent is a common one. Intermittent motors are designed to be started and stopped all the time. Continuous duty motors are good motors. It's easy to run continuously. It's harder to start and stop a motor. So the intermittent duty motors are built with a little more substantial wiring and things like that. Well, thanks for joining us for another episode of MyToolboxTV. Hopefully you learned a little something about motor nameplates. Something I recommend further for you to do right now is go to NEMA's website, look at all those charts, go to manufacturers' websites, look at manufacturers' catalogs, learn all the data that you can about these motors. Look at what's available. See what the standard horsepowers are, the standard RPMs. Learn as much of that kind of stuff as you can. The catalogs are a great place to learn from. They're the best textbooks there are. Thanks for joining us. Until next time.